the future of production rendering from Pixar, adding GPU acceleration to RenderMan. And I put that smaller there, and because I'm going to see later why. So before I start, I would like to thank like at least 3 people. This talk is short, so I'm going to thank only 3. That's Mark Bannister, Charlie Kilpatrick, and Cliff Ramshaw. Without their hard work, I wouldn't be here presenting this today. So in this talk, we're going to talk about a technological journey that started a long time ago, and in particular, all the advancement in real-time graphics and the use of GPU at Pixar Studio, which is, let's say, like our starting point. We're going to talk about RenderMan. So I would like to ask you, how many of you are graphics engineers or involved in graphics? Please raise your hands. Like a fair amount, let's say like half of you. So I'm going to try to explain a few things here and there just to make things clearer, but I'm going to try to not overboard with explanations, some things to not bore anybody. So we're going to talk about RenderMan. We're going to talk about the way of GPUs for high-end graphics, and by high-end graphics in this case I mean frame finaling, producing the image that then you see in the theater, and what all of that means. What we are not going to talk about is a sales pitch. I'm not here trying to sell you a product or tell you that it's finished, go and buy it, like none of that. I'm going to show you some pictures that are made with RenderMan just as an example of what RenderMan is used today, but I'm not going to tell you that this is a finished product. I'm not going to show you a feature matrix and comparison or things like that. Not everything is going to be easy, and not all problems have been solved. So with that, just a quick introduction. What is RenderMan? RenderMan is a production photorealistic renderer that is based on path tracing. It is used to render every single frame that has ever been made by Pixar, and much more, because RenderMan is used by many studios around the world. And not only studios, it's used for scientific visualizations and other things that goes way beyond movies and entertainment. So I said it is a production render. So what is a production renderer? There are many renders out there, and pretty much all of them can make good photorealistic pictures, but not all of them are robust and battle-tested to deliver entire movies. Although there are a variety, there are several of those, and you probably have seen presentations today, and you get to see what all of these are able to do. So a production render is able to handle extreme complexity, because that's what you see in those, like in movies and visual effects. They have to be ready to be shaped and framed together into existing production processes. So they have to be customizable and adaptable, and they have to be extendable with depending on the technical resources of different studios, they might be able to do development. So this is how RenderMan is used today by some of our customers, other than and Pixar. Okay, so I've shown you this not to promote RenderMan, but to give you a sense of what RenderMan has to do on the GPU moving forward. So I want to introduce quickly RenderMan XPU. It's our next generation renderer. It's a brand new renderer based on RenderMan. It means that it's going to use the same scene description, the same way for the users to operate it, but is a brand new implementation. So this is GPU and CPU that can render separately. So you can produce like a frame entirely on a GPU or entirely on a CPU, or both rendering combined to combine the speed. And produce perceptually identical results, which is super important if we want to be able to render in two different hardware architectures. So here in our example, we have a Coco production asset that is not as it appears in the movie. I modified it a little bit. There were some parts that were rigged and I couldn't move them, so I just removed them, like the pantograph. And one side you see the GPU render, and the other side you see the CPU render. These are both produced by RenderMan XPU. And just to make it simple for you, CPU, GPU. Okay. So they're absolutely, they're almost identical. There are some cases where things can go a little bit off. If you are curious, you want to know about it, ask me a question later about cases where it can go wrong. So what changed? And that's pretty much everything. And that's why the title at the beginning, like adding GPU acceleration to RenderMan, doesn't really work, because you don't add a GPU acceleration to a complex product like this. So you have to rewrite it in full to really be able to shine. So we keep the front-facing control, the scene description, all that stuff that the users know and I know how to operate. We replace everything else. So why GPUs and CPUs? That's a practical and pragmatic choice. A product that needs to render today needs to run on existing hardware, so that we offer an opportunity to our customer to decide where to invest. You know, GPUs are going to provide this beautiful, like amazing speed up. They can evolve at their own pace and decide where to put their investments in the new purchase. But they need to use what they have today if they want to use it today. But isn't this twice as hard to architect and put together? Well, it depends on really how to put it together. So we have a shared implementation between CPU and GPU. Our target is C++ and CUDA. And CUDA is basically C++ with extensions. So this marriage works very well. It improves consistency. It reduces our development cost because we don't have to implement things twice. And it reduces the bookkeeping or debugging when one bug might show up in one of the devices and not in the others, or like a visual defects. But of course, not all algorithms can be implemented sharing the same code base, the very same algorithm between CPU and GPU, so we need to be able to specialize them. And we do that by using a nice legal trick delivered by C++ templates, which are supported in CUDA. And so we can use a device type as a template specialization or partial template specialization. And most of the code is shared apart from what is very specific and requires that targeted optimization. So I'm going to show you like a little snippet of code, and this is how technically I'm going to get. And because it's a short talk, I cannot explain pages and pages of code. So I'm trying to make it as simple as possible. So at the top, we have a simple template compute value. It does something. We put some code in there that will compile and run on CPU and GPU. And at the bottom, we have a template specialization where we say device type GPU, and then we insert function calls that are specific to GPUs. We can use like a library that are only available on GPU. We can call optics in there and make use of like a ray tracing call accelerated by optics. While on the CPU side, we will have something else. And we can not only specialize between CPU and GPU, but even different across microarchitecture. So we can have a partial template specialization that is just for Volta and another one for Pascal. and the rest of the code or the rest of the kernels are all identical. So we talked about, like very briefly, about how we can do CPU and GPU together and what we can develop this technology moving forward. But we haven't talked about how we solve the prime problem, which is scaling to complexity, which is what RenderMan do, or asked to do. So this is a scene from movie Coco. This is the train station on the Land of the Dead. Is 27 odd, like point lights. There is complex geometry, characters. There is, like you name it, is all there. And this is what we need to render on the GPU. So spoiler, I'm not going to show a frame like this rendered on the GPU because we're not ready. But I'm showing you like a little bit and pieces of like the technology moving forward. So this is a 4K render in XPU using just diffuse illumination on a Quadro GV100 card. This is the very same geometry that is in that frame. We have all sorts of things. Let's show like some close-ups. Very intricate architecture. We have crowd with high-resolution cloth seams. There is everything in there. Like this scene here is composed by 145,000 individual objects. Only the poly cage is about 174 million triangles before subdivision surfaces. So looking at this scene when I was preparing this slideshow, one name particularly caught my eyes. That's my favorite object name, and this light bulb filament. You can see them from other angles, not from this one. But they're there. Every light bulb has filaments there. So why do the artists do this? Well, don't really ask me. But this is what our clients do with RenderMan today. And we have to enable them to do this on the GPU tomorrow to support this beautiful level of madness. That scene doesn't come up easily from like a geometric description. So we have a new geometric engine. It's a high bandwidth geometry processing API that is fully multi-threaded from data ingestion on. It is designed for live rendering, so nothing is baked in, nothing is collapsed, everything is live. You can zoom the camera in, you can move a vertex of one geometry and move on into the next edit. We use clever data compression techniques to cream as much data as possible into those devices. We offer buffer paging, although we are not leveraging buffer paging for ray tracing yet because we want to see how much we can push the data compression techniques. The shading system, and I'm accelerating here because I see that time is flying. The shading system is based on open shading language for pattern generation so that our user can write whatever the shader they want. And open shading language uses LLVM JIT compilation to compile to NVPTX and x86, which gives us exactly the same shader code running on both devices. I have to thank NVIDIA for all the hard work championing the porting of this project to the GPU. A texture system relies on textures, and if there is something more than geometry in those scenes, this is texture. Device memory is premium. We have a limited quantity, and the texture data sets tend to be huge. Hundreds of gigabytes, even terabytes on a shot these days. Typical texture are 4K square, so 4,000 by 4,000 resolution, or 8K. We start to see some 16K square, all the way up to 128,000 by 128,000 square. Crazy artists actually know that particular texture that we saw comes from one of our scientific clients, NASA, which is rendering scientific data sets and high-resolution geospatial scans. And they use those textures, which, of course, are in full floating point precision. So imagine 128 square full floating point precision, how big that file is. So our texture system, we have different choices that we can try, that we have tried. And one is preload everything, but with 128K square, you don't load anything, so it won't scale. We could do statistic analysis of the scene to figure out which discrete downsized version, mip-map version of the texture to load. But with live rendering, when we move the camera, we need to be able to pull in data that is very specific to how like the ray hits that surface. So again, not really a solution. Caching and streaming sounds hard, so let's do it. So the texture system is based on texture caching and streaming. The tricks are not that new. We use ray differentials to choose the appropriate mip-map level, so to choose which resolution and which tile within a texture we need to load. We have a two-level caching because when you think about out-of-core data, when you're on a CPU, the out-of-core data is disk or network. But when you're on a CPU, typical out-of-core data is on a CPU. So here we have like 2 hops to get to the data. And so we have like a system memory texture cache and a device, per device texture cache. And the trick here is to run the pattern evaluation up to feeding the texture request, collect all the texture tile requests, streaming the data that is not in cache, and continue pattern evaluation. Can we get this thing to scale on a device by reserving, like let's say 500 megabytes of memory? And let's make the test as prosaic as we can possibly imagine it, which is many spheres. Spheres, each one with a different texture, and how much of data can we access efficiently using that 500 megabytes of cache on the device. And so this is the first test, and is about 70 gigabytes of high-resolution texture data. Of course, we're not reading in 70 gigabytes. We're allowing the system to decide what to pull in. And so each of these spheres have a different file, like between 4K, 8K, 16K, etc. Some files look exactly the same. They are actually animated textures, different frames of animated textures. So let's double it up with more walls of spheres in front and more and more. So here we go. We have 280 gigabytes of texture data that we render with only 500 megabytes on the device. And when we zoom closer, we see that those textures are actually, higher resolution. We can zoom in closer. So we pull in only the texture that is necessary. And that texture there on the sphere is like an actual 8K by 8K. That's the detail of that texture. And only what is necessary is put in. Like I want to go back one slide and show you how this test here is actually not naive. Each of the spheres in the back is reflecting about 2,000 different spheres with 2,000 different high-resolution textures. And the system needs to be able to pull in and streaming in with this like very sparse data access. So was it just putting together the texture system enough? Actually, not really. We need to go deeper than that. And we're talking about the texture system to the texture format. At the rate at which the GPU is consuming data, the texture format needs to be high performance too. And most of the file format that we have today has been designed decades ago. So we have TIFFs, we have AXRs with data encoded in a variety of ways. They are slow to read. Each of these files is structured more or less like this. So we have a file header at the top. We have an 8K image followed by a 4K, a 2K, and scaling it down. Often there is metadata interleaved between those tiles because those are image file format. They're not texture file format. So image file format, these are different images stored in chain one after the other. So what we're going to read is the file header, and the data that we are likely going to access is right there at the bottom. And so we open the file and we read a chunk there. The operating system will think that it wants to outsmart us, and it's going to read a chunk of 8K file that we don't need. And then it's going to read somewhere in there, reading for metadata, and there, and there. And eventually, when we render, we're going to access the data at the bottom. And all of that is all wasted. Apparently, opening a TIFF file or an OpenEXR is just to open the header is like more than 100 different reads. So not particularly fun there when you have to open tens of thousands of different files and let it start like that. So how about we flip it upside down so that when we read something, the operating system does the smart thing and pulling in the data that we actually need so that next time we go and access something, is most likely going to be there. This is just really the tip of the iceberg. There is a lot more to do and a lot more that we could talk about, but I'm kind of like slightly going out of time. So light transport, light selection, volume rendering, these are all challenging things that are worth discussing, and we're sure we are going to do further presentation moving forward. So just to remind of where we started from, these are the requests that we typically get. Can we render really intricate architecture, vehicles, a large crowd of characters and creatures illuminated by millions of light sources? And we want to say, sure, bring it on. And this is just a reminder of what we are going to support. This is the length of the DAD in Cocoa. And this is a single pass render. Has been subdivided in different contributions just to show it, but it's rendered as a single pass. So, questions?